acids and bases come in a couple of different types, right? We've got strong acids, we got weak acids, and we got strong bases, and we've got weak bases. And those guys are going to be defined in a couple of different ways. We've got Bronsted-Lowry, we've got Arrhenius, and we've got Lewis. 3 different ways to define something as an acid or a base. The Bronsted-Lowry is the simplest. It's kind of the OG definition for what makes something a acid or a base, and it's all looking at the protons, right? It's all proton centered. Right? So in Bronsted-Lowry, an acid is a proton donor, and a base is a proton acceptor. So if you think of something like HCl, which you should know is an acid, right? Hydrochloric acid, is able to give up a proton, which means that something like potassium hydroxide over here is going to be able to form a reaction where we've got the H plus reacting with the OH minus to give us dihydrogen monoxide. Right? So this hydroxide is going to be a proton acceptor. If I've got something like ammonia, right, it can pick up a proton and it can form ammonium. NH4 plus, right? So the ammonia is acting like a base because it can pick up a proton. Ammonium, if I put that in solution, will give up a proton. It'll be a weak acid. So if you look at a solution that contains acetic acid and potassium hydroxide, the principal species in solution are this acetic acid, potassium, and hydroxide. Precipitation doesn't occur because our potassium hydroxide is soluble. Not all hydroxides are soluble, but we got a group 1 guy over here, potassium, so it's going to be soluble. Right? And those OH ions are capable of attracting protons from your acetic acid. Right? Another definition of our acids and bases is the Arrhenius definition. So our Arrhenius definition is a substance that dissociates into water to produce H plus hydronium ions. It's actually H3O plus. H3O plus. You're not going to have a bare proton floating around. And the hydronium is going to have a Lewis structure that looks like this, where we've got water. It looks like it's going to pick up a proton. And it's going to form this H3O plus, where it's going to have a tetrahedral electron domain geometry, but once it picks up that extra proton, it's going to go from a tetrahedral electron domain geometry. It's got 3 atoms around it, so it's going to form this kind of distorted trigonal pyramidal structure. That's what it looks like in Lewis structures. So that's a little bit more advanced version. We're just going to write H plus because we're going to be lazy, and it saves us from having to write out H3O plus. And even this is a little bit of a fiction. So hydronium kind of doesn't exist like this in water. It actually looks like this over here, where you've got this extra proton and it's almost constantly playing like a game of hot potato with all of the other waters in there. So this extra proton just kind of zips from one to another. And there's whole bunches of stuff where people have done studies on like, well, how fast is this proton moving? And is it really this proton? Or is it like this proton goes from here onto this guy and it kind of kicks this guy off? So there's a constant motion of these protons in solution. But our definition of an Arrhenius acid is something that makes H plus in solution. So we can give it a generic form and call it HA, where this A stands for the rest of the acid, and the H plus is our labile or proton that can come off. And for example, HCl is going to dissociate into H plus and Cl minus. In water, you're going to produce these hydronium ions, right? And they kind of don't look like that, really. It's going to be a little bit more distorted, and really it doesn't exist except as this kind of hot potato thing, right? An Arrhenius base is something that dissociates in order to generate hydroxide ions, or OH minus ions. So generically, it's going to be some sort of metal hydroxide. So, you know, a group 1 like sodium, or a group 2 where you're like... calcium hydroxide, or barium hydroxide, or strontium hydroxide. It's just that those guys are going to have a formula that'll look something like this, right, where it's going to form two hydroxides. Ammonia, commonly called ammonium hydroxide, is a weak base. Right? It is able to react with water, pull a proton off of water, and form hydroxide, which is a strong base. And over here we've got ammonium, which is a weak acid. And a fight between a strong base and a weak acid, which one do you think wins? It's going to be the strong base. And so ammonia in solution is going to be weakly basic. Our most general definition of an acid or a base is our Lewis definition. And as you might suspect, it is all about the electrons, right? Because Gilbert loves him some electrons. In a Lewis acid is an electron acceptor, and a Lewis base is an electron donor. The acid accepts, A and A, the base donates. That's the best I can get for that. And the reason why this is a good general definition is your Bronsted-Lowry and your Arrhenius, right? These guys work great in aqueous solutions, but you can still have stuff acting like an acid or a base in a non-aqueous solvent system. So if you're doing something in hexanes, like you're doing organic synthesis, and a non-polar solvent, right, like benzene or hexane as your solvent, you don't have a bunch of hydroxides floating around. You might have some protons moving around, but not always. And so this Lewis method or Lewis definition, where we're looking at the movement of electrons, either as an acid accepting electron, so like H+, that wants to pick up some electrons, right? So all of these definitions will match each other. It's just that they're getting more and more general as you go from Bronsted-Lowry, as you go from Arrhenius to Bronsted-Lowry to Lewis, right? Lewis is the most general, but it's also kind of the hardest to conceptualize. The Arrhenius model, that's our oldest, it's our most specific, but it's easy to figure it out, right? Acids make protons, bases make hydroxides. And here is a table of some common acids. We've got both strong acids and weak acids, so things like perchloric acid, sulfuric acid, hydrobromic, hydrochloric, nitric acid. Those are all strong acids. I will ask you guys to memorize some strong acids and strong bases. So this chapter is a little heavier on memorizing than some of them, but memorize some strong acids and some strong bases. Right? Our strong bases are going to be real easy. They're just like all of our alkali metals with an OH stuck on them. That's so sodium hydroxide, potassium hydroxide, lithium hydroxide, and then some of our alkali earths. Right? Barium hydroxide and strontium hydroxide for sure. Calcium hydroxide to the extent that it dissociates. So calcium hydroxide is not going to be super soluble, but to the extent that it does dissolve, it's going to generate two hydroxides. It's going to be a pretty strong base. Right? We also have weak acids and weak bases. So phosphoric acid, hydrofluoric acid, acetic acid, those are all going to be what we call weak acids. They're not going to completely dissociate. We're going to have weak bases. They're not going to completely dissociate. These guys up at the top, our strongs, would be strong electrolytes, and our bottoms would be weak electrolytes. So here's another representation of our strong acids and strong bases. So you've got your easy ones over here, right? These guys with the H and then a halogen. So we call these HX, where this guy is a halogen. Like, right? These are going to be called hydrohalic acid. Right? And so it's all of the halides with an H stuck on them, with one exception. So not hydrofluoric acid. Hydrofluoric acid is a weak acid. That's part of why we put the fluoride in toothpaste, is because you form fluorohydroxyapatite instead of hydroxyapatite on your bone enamel. It's a weak acid. It doesn't want to dissociate. I met the guy who put the fluoride in toothpaste. He was a really nice, sweet old man. But HF is a weak acid. This guy is weak. It's a plenty nasty acid. I would much rather stick my hand into a container of 1 molar HCl than 0.01 molar HF. HF is used as a glass etchant, but it will also do really nasty things with your biochemistry, and it will start to really just glom up all the calcium that you've got, and so it's really, really painful and can actually kill you. So HF is not something I will work with without a lot of protection. HBr, HI, this guy over here, HNO3, that's nitric acid. Then you've got your guys over here. They're going to be with our perchlorate and chlorate. This guy right here, H2SO4, that is sulfuric. Right, so a good test question, if I'm looking for 5 or 10 points of a test question, give me 5 strong acids, give me 5 strong bases, give me some weak acids, give me some weak bases, right? Our strong bases, right? Lithium, sodium, potassium, rubidium, right? These guys are all my alkalis, right? And then we got these other guys over here, to the extent that it does, kind of, and then our alkali earths, right? So, 1, 2, 3, 4, 5. Right? 1, 2, 3, 4, 5. Right? Easy. Right. A lot of our oxo anions are going to form acids, corresponding acids, when we stick a proton on there as the cation. So if we've got HNO2, that's going to be nitrous acid from nitrite, and nitric acid from nitrate. Right? This guy is going to be strong. Right? Phosphoric acid. This is what does a lot of the damage to your teeth when you're drinking soda pop. Right? Phosphoric acid. Sulfurous acid from sulfite, and sulfuric acid from sulfate. That guy's strong. Hypochlorous acid from hypochlorite. Chlorous acid from chlorite, chloric acid from chlorate, this guy's strong, perchloric acid from perchlorate. And then over here we've got nitrite ion, nitrate ion, these are the corresponding acids. Okay? So if you've got an ite, you become an us. If you got an 8, you get an ick. Right? So if you ate too much, you get ick. And then you realize the other one is the opposite of that, right? So your ite becomes the us. Right. Our binary acids, or hydrohalic acids, are going to be hydrochloric, hydrobromic, hydroiodic, and then hydrofluoric. But keep in mind that this guy here, right, is an exception, and it is weak. Okay? So what do you do with these acids and bases in solution? Well, if you mix them, you're going to get an acid-base neutralization reaction. They are double displacement reactions, just like precipitation reactions. It's just that we are going to have water pretty much all the time as one of our products. So we'll form HOH, dihydrogen monoxide, and then we'll have the leftover parts of our acids and bases. So remember, our very simple definition of an acid is something that produces a proton, and our base is something that produces a hydroxide. We're going to end up with HOH as one part when they do their do-si-do, and then we'll end up with M and A as being our other parts. All right, so whatever our metal is, and then whatever the rest of our acid is. So we've got HA as an acid, and MOH as a base, so something like sodium hydroxide. Right? And so this is your go-to strong acid, strong base reaction. HCl, hydrochloric acid, reacting with sodium hydroxide to form a salt, in this case, NaCl, table salt, and water. Now this is only going to work for strong acids and strong bases, that you get a salt and water. All right? You're going to end up with leftover conjugates if you're dealing with weak acids. All right? So if you've got a strong acid and a strong base, you end up with salt and water. But what happens if you've got a weak acid and a weak base? The conjugate is what gets left over and remains in solution. So if I take HCl, which is strong acid, and I react it with ammonia, which is a weak base, I'm going to have ammonium left over. Right? This is my conjugate weak acid. And over here, this chloride is going to be our conjugate weak base. Right? The chloride ion is not going to affect our pH at all, but my conjugate weak acid will. So if I react equal amounts of HCl and our weak base ammonia, I'm going to be left over with some ammonium, which will be slightly acidic. If I take acetic acid, which is a weak acid, and I react with sodium hydroxide, which is a strong base, I will have leftover water, which is neutral, sodium plus, which is neutral, and acetate, which is our conjugate weak base, so this solution will be weakly basic when I'm all done. And this guy up here, I remember we said that guy was weakly acidic. So our net ionic reaction for one of these neutralization is going to look like this, right? We've got our hydroxide, right? That would be coming from a strong base. And it's going to react with acetic acid. That's a weak acid. We will form water, right? So our HOH is going to react with this. And then whatever our conjugate was over here, we don't care about that. But over here, we're going to end up with this guy as my conjugate weak base, right? And this guy will be our conjugate weak acid. Now, water is neat stuff because it's what we call amphoteric. Amphoteric means that it can be either an acid or a base. Water can give up a proton and form hydroxide, or water can pick up a proton and form hydronium and be an acid. So water can swing both ways. Right? For purposes of stoichiometric calculations, it can be assumed that the OH ions react completely with any of the weak acid, and our acid-base reactions are called neutralization actions because they are driving towards a neutral pH of 7. So when you're doing an acid-base calculation, you're going to list all the species that are present, combined in the solution before any reaction occurs, and decide what reaction will occur. So in this case, it's just the same setup. It's just that rather than looking at a precipitate, we're going to form liquid water, and then we're going to see what stuff is left over. Right? You're going to write out the balance and net ionic equation for this reaction. You're going to calculate the moles of reactants, right? Probably going to be hidden as a volume and a concentration. You'll determine the limiting reactant if one runs out first. You'll calculate the moles of the required reactant or product, and you'll convert to grams or volume or a concentration, right, depending on what the question's going to ask you. So let's look at an example. What volume of 0.1 molar HCl solution is needed to neutralize 25 milliliters of 0.350 molar sodium hydroxide? Again, step 0 is going to be write out that balanced chemical equation, and then also if you've got moles hidden with a volume and a concentration here, right, that guy's going to be moles, right? So you want to get your BCE, right? Then you want to get your moles. Okay, let's follow what they're going to do. So our objective, we want to find the volume of HCl required for neutralization, right? So remember, this guy's going to look at volume, right? We can rearrange that and say our volume is going to be equal to our moles divided by our concentration. And again, that's just rearranging our original moles is equal to, molarity is moles over volume. So we want to find the volume of our 0.1 molar HCl. We are told that we've got a volume and a concentration of hydroxide. We know the concentration of HCl we've got. We're going to write out our balanced chemical equation. Real easy with the strong acid and strong base if we're looking at our net ionic equation, right? Our net ionic equation for a strong acid, strong base reaction is just H plus and OH minus gives us H2O. All right, so we're going to identify the ions that are present. We've got H plus, we've got OH minus, we've also got these guys as spectators. We're not going to care about those. So the two possible reactions are either that my NaCl is going to react to form NaCl solid, which doesn't happen, right, because all chlorides are soluble, and all sodium compounds are soluble, so our precipitation won't happen. And then we've got H plus and OH minus, and that most definitely is going to form water. So our balanced chemical equation is going to be H plus and OH minus, gives us H2O liquid. Then we're going to determine the moles of reactant present. So we got our 25 milliliters of sodium hydroxide. We convert that into liters. Our milliliters cancel out. We then multiply that by our 0.350 moles of hydroxide per liter. Our liters cancel out. We end up with 0.875 times 10 to the third moles of hydroxide. And then we're going to figure out what our limiting reactant is. This requires the addition of just enough H plus to react exactly with the OH minus ion presence. We don't have to figure out a limiting reactant. All right? To figure out the moles of H plus required, since the H plus and OH minus ions are going to be in a 1-to-1 ratio, our 8.75 times 10 to the minus 20 times 10 to the minus third moles of H plus are required to neutralize the hydroxide ions that are present. So then we got to figure out the volume. So our volume times 0.1 moles per liter is going to equal 8.75 times 10 to the minus third moles. Rearranging that, we're going to take our moles, we'll divide it by our concentration, and we'll end up with 8.75 times 10 to the minus 2, or 8.75 milliliters. Right? There is another way to do this. All right? You can, and I'm going to write this in yellow or orange, right? Because it's kind of a little dangerous. You can sometimes use your dilution formula. M1 V1 equals M2 V2, right? Because this and this, volume and concentration, is moles, right? If I'm looking at my moles of hydroxide, when I neutralize that, I've got equal moles of hydroxide as I've got moles of H+. So I can still use this dilution equation to do it, but there's some caveats, right? It's got to be 1-to-1 stoichiometry, right? You can't just go using this all the time. This way here, where you're kind of breaking it out step by step, right, is a little bit more sure. Doing it using a M1C1, M2C2 type of deal will work a lot of the time, but not every time. So it's a little bit dangerous to use, but if you get stuck in a jam and you're like, I don't know, what do I need? I'll try doing this, right? So I'm putting that out there as another tool in your toolkit, but I want you to be careful using it. Just because you got this equation doesn't mean it's appropriate everywhere. Just because I give you a hammer doesn't mean everything is a nail, right? So you may have a hammer, but if you go in to do chiropractic work, please don't bring your hammer, right? So what else can we do? We can do something called a titration. We got a couple of different types of titration that are out there. Titrations are going to fall under the broad class of what we call volumetric analytical techniques. There's several classical techniques like volumetry and gravimetry, but volumetric analysis is going to be using volumes of liquid, right? And it's easy for us to measure liquid volumes. To determine the amount, right, it's going to be quantitative, and how much of a certain substance by doing a titration. Now, a titration, sometimes abbreviated TTN, is the delivery of a measured volume of solution of known concentration, that's the titrant, into a solution containing a substance to be analyzed, and usually you know the volume, and you find the concentration of your analyte or your unknown. Right? When we do this, we want to put in an amount of titrant that is going to reach an equivalent point, a stoichiometrically equal point to whatever our titrate is. So when we set these guys up, in case you have not seen one, you're going to have some sort of burette. It's a piece of glassware that looks like this. It's a big tube. It's got some markings on the side. It usually has some sort of stopcock for delivery. And you're going to add this to some sort of reaction vessel. Right? And you'll have some unknown, you'll have a solution in here where your concentration is unknown, but you're going to have some sort of known volume, like 10 milliliters. And in your titrant, you will know its concentration, like 0.1 molar, and then you will measure a volume. So you've got a volume and a concentration here, that's going to be moles. In here, you've got a unknown concentration and a known volume. So you can set this guy up like this, where in your titrant, you've got some sort of measured volume, and you've got a concentration, right? And that's going to give you some number of moles. And then that number of moles is going to be equal to the moles of your titrate, right? And you're going to have some sort of volume and then some sort of concentration. And usually you were trying to find this guy out. You're missing concentration. Right, so you got a titrant and a titrate. And you put this guy in, drop, 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 until you reach the endpoint. And oftentimes we'll do that with an indicator. So you will probably do one with phenolphthalein, where it's going to go from clear to pink when you've reached your endpoint. That's the stage. The endpoint is where the indicator changes color, and that's going to usually be close to what the equivalence point is. An equivalence point and an endpoint are not the same thing, right? So they're not the same. Right? Your equivalence point is talking about moles, whereas your endpoint is when the indicator changes color. Right? So two slightly different things. The exact reaction between the titrant and the titrant has to be known, and hopefully pretty quick. The stoichiometric or equivalence point must be marked accurately, and the volume of the titrant required to reach the stoichiometric point must be known accurately. And I will post a video about doing titration so that you guys can watch that separately.